Hi everybody. So we are done with ray optics. So today I am going to start the next optic, that is wave optics. So before I start wave optics, let me have a brief introduction about wave optics. So let me start introduction something like this. It means now we are trying to understand the nature of light. So the first theory of light, the first model of light was proposed by René Descartes in year 1637, and his model is what we call as corpuscular model of light. So according to his model of light, he says that light is particle in nature. So corpuscular means a particle, right? So light is a discrete, a particle in nature. And light comes in a stream of particle. Light comes as a stream of particle, and light goes straight. And using his model or theory, we could derive a Snell's law. And when a light goes from air to waters, it bends towards normals. However, when he used his theory, it was found that the speed of light in water is going to be higher than the speed of light in air. And then his theory was further developed by Isaac Newton, and in his book entitled Optica. All right. So his theory becomes so famous in around year 1600. All right. This is the one aspect of a light. All right. And now the second model of light, that is the wave model of light, was first put forward by Christian Huygens in year 1678. All right. And this is all about the wave model of light, or that means the wave theory of light. And when we use these theories, we could again explain a phenomenon like refractions, reflections, Snell's laws, and all. However, when we use these theories, we could able to find that the speed of light in a water is less than the speed of light in air, which contradicts the dynamic or corpuscular theory of light. And then later it was experimentally found that speed of light in a medium, that is water, is less than speed of light in air. However, his theory was not become so famous in year 1600, and then I say why his wave theory was not readily accepted by people during those days. Some factors such as whenever we talk about wave, we require a medium to traverse, or a wave means a disturbance. That is discussed in the class 11, that a sound wave. So therefore, a light could traverse even without mediums. So therefore, this is the one difficulty in his theory, that how light could travel without medium. All right. And then later he just assumed a hypothetical medium like ether mediums. All right, this not maybe beyond our scope. All right. And then second difficulty is that Isaac Newton was so famous during those days. Therefore, the particle nature of light, that is a corpuscular theory of light, becomes so famous in year 16 around. All right. However, the Christian Huygens theory become something like not aware. It was not become so famous as like corpuscular theory. However, in years 1801, it was Thomas Young who performs a very interesting experiment or interference. All right, and Thomas Young could perform the interfering experiments using a light, and this proves that light has wave nature. Alright, this proof the beyond the doubt that light has a wave nature. Light has wave phenomena. Alright, so therefore, after Thomas Young's, many scientists are doing experiment on wave nature of light. Many people could found a diffraction for light, interference for lights, and then more in the mid 19th century, it was James Clerk Maxwell who put forward a most important theory of a wave, that is electromagnetic wave theory of light. Alright, according to his theories, he says that light doesn't require medium to travel. He says that an electromagnetic waves or light is associated with electric field as well as magnetic field. Light is associated with changing electric field and changing magnetic fields. And how light propagate? His theory says that changing electric fields give rise times and a space, changing times and a space of magnetic fields, and changing magnetic field give rise to changing time and a space, time and space changing electric field, and this is how light could propagate in a space. Therefore, it says that his theory says that light doesn't require a medium. Even his theory could explain the speed of light. Alright, so and James Clerk Maxwell could discover a new wave called electromagnetic wave, and the light comes under electromagnetic waves. Alright, so therefore in mid 19th century, the wave nature of light becomes so famous. Alright, having so many evidence, now people believe that light has wave nature. Alright, or light is electromagnetic wave, which doesn't require mediums, which is all about changing magnetic fields and changing electric fields. They regenerate each other. Changing magnetic field give rise to changing electric field. Changing electric field give rise to changing magnetic. This is how light propagate in a space, even in a vacuums. And now this is the point. This is the other aspect. So this is the Maxwell gives what we call electromagnetic theory of light. And Christian Huygens gives, alright, the wave theory of light, and more the Christian theory of light, Christian Huygens theory of light is more towards a mechanical wave. He assumed that light is mechanical waves. Alright, so in this chapter, what we are going to study is we are going to study many phenomena such as reflections, interference, diffractions, and polarizations, keeping that light is wave, that too the Huygens concept of wave, not electromagnetic wave. The Huygens concept of wave, that is what we call the wave front. Wave front. This is what we are going to study, right? So this is all about the introduction part. Alright, this is all about introductions. Now I would like to start with a chapter that is what we call as a wave front, Huygens principles. Huygens principle. Alright, so this is very, very important concept, without which we won't able to proceed next topic. So this is what I have. So as I told you again, Huygens assumes that light has a wave, that is mechanical wave. Huygens talks about mechanical wave. Huygens never talks about electromagnetic wave or non-mechanical wave that we have studied in class 11. Huygens talks about a mechanical wave, and Huygens concept about wave is all about geometrical constructions of a wave. Alright, now let's start. I have a calm pool of water. If I drop a small stone on a calm pool of water, what do we observe? This is what we are going to observe. And we see, and then I disturb a water, and then you find so many rings of water, waves coming out. We call it as a wave. Waves coming out, right? So many rings, right? This is what we call as so many circular rings are coming. You find so many circular rings comes out, and this is how it goes from the point of disturbance. And we also studied in the class 11 that all these rings, all these circular rings are what we call as disturbance. And all these rings, undergo oscillations. That means it's vibrate, it oscillates up, down, right? So that is how. So when I take a snapshot, you are going to find this. And I said all these circular rings are what we call as a ripple normally we call it a ripple, and we call this as a wave forms. And waveform is nothing but disturbance. This is what we call. So that waveform goes away and goes. If I continue disturbs, you find so many rings, circular rings coming out from this source, and this is how wave goes out. This is how wave propagate in a water. All right. So we say that these circular rings are what we call as a waveforms, and this is how it goes. All right. I have another examples. Now look at here. I go on disturbing periodically, and we find a beautiful rings of circular rings are coming out, and each ring. Look at here. All right. Each ring. When you observe very carefully, each rings go up all together, goes down all together. That means they oscillate in phase. All these. Alright? Water particles all along these rings. Alright? Water particles, so water molecules lying all along each rings goes up at the same time, goes down at the same time. So therefore what we call as oscillations. And water molecule doesn't move. And what is moving? The disturbance is moving. A waveform is moving. Alright? Water particle goes on oscillating up, down, and oscillating. Alright? And this is what we call that all water particles lying all along particular rings are in phase. In phase means they all go up together, go down, and come down together. This is what we have. And this is again here also, right? If I observe, goes up and goes down. Alright. So this is what we have. This is the nature, right? This is the nature, right? So this is waveforms, and all the water particles lying on each waveforms are going up. Same time goes down, comes down, at same time. This is what we call as in phase. Again, I have a better diagram. So this is water, and these are what we call as a waveform, which I told you before, right? Alright. So this is what we call a circular waveform. See, this is a plane. Water surface is a plane, therefore we could observe only circular waveform. Right? So all the water particles all along this goes up, down. At the same time, this is a particular waveform number 1, this is waveform number 2, this is waveform number 3. And this is first it creates and then goes to this and goes to next, goes. How wave progress. So therefore, now what do you mean by waveform? Alright, what do you mean by waveforms? So waveform is defined as a locus of points oscillates at same phase. a locus of points which oscillates at same phase. That means, look at here, a locus of point is a set of point which satisfy certain conditions. What conditions? They are in same phase. They are at same phase, right? Oscillate at same phase. They all go up and down with same phase. This is what we have, right? This is what we have, and then this is what we call as wavefront. This is circular wavefront. This is what we have, circular wavefront. Again, I have a nice diagram, and this diagram is nice, right? This is how it propagates. So this is the first wavefront, then this produces the second wavefront, and that produces the third wavefront. This is how wave travels. And this is how wavefront travels. Wavefront travels from one point to another point. Again, I'm telling you, the water particle doesn't travel, the wavefront travels. So wavefront is one and the same. Wavefront is equivalent to disturbance. Disturbance travels. This is taught in class 11. Disturbance travels, but water particles doesn't travel. So therefore, wavefront travels, right? And this wavefront generates next wavefront. This wavefront generate that wave. This is how it travels, right? Like this. I have given this a beautiful diagram. So this is how we define a wavefront. A locus of points which oscillate at the same phase. Or again I define as it is a surface which has constant phase. A surface which has constant phase. So this, I consider this as a surface which has a constant, that means they all go together at the same time, all comes down at the same. This is what we call as wavefront. This is what we call as wavefronts. Again, you just put in alright, so this is how it goes. So this is, I have written like a circular wavefronts, and this is source is, I go on dipping the finger in a water, and that produces this disturb waters, and wavefront travels. This is the shape of a wavefront. This is how wave travels. The wave travels in a direction perpendicular to the wavefronts. Alright, so this is what we have. A wavefront is a line that joins all the peak of a wave or all the identical point on the wave. That's really what we have done. Alright, so this is for water wave. This is for water wave. Alright, so keeping water wave, I am going to apply this to light wave. This is what we have. Now, I said, I have a light. Consider a light. If I put on the light, and instead of a plain circular wavefront, you are going to get a spherical surface. The spherical surface is what, this is a three-dimensional surface. This is a three-dimensional surface. So look at here, this could be let's say a source of sound. Here I say it is a source of light. When I put on the light, light in a homogeneous space, and light travels, alright, in three-dimensional, right? So look at here. If I choose this surface, how many surfaces are there? One surface, two, first, second, third, or fourth surface. Alright. This is how light travels. This is how light travels. This is how light travels. And now look at here. I just take this surface. Alright. The light on this surface are all oscillating. Alright. Light on this surface are oscillating with, oscillating with same amplitude, and same phase, and oscillating with same amplitudes, and then vibrating with amplitudes, and oscillating with same phase. Let's say equal amplitudes and with same phase. That's what we have, right? So now instead of a water wave is, this is a plane surface. Now it is not a plane surface. This is a three-dimensional space, and water. The light goes out. All right, and this is the first spherical surface. This is the second spherical surface, and this is the third spherical. And such a surface, I choose a surface. That is a surface. I choose a surface where you find a light oscillating with the equal amplitude in the same phase is nothing but a spherical surface. You get a spherical surface which you see here. You get 4 different spherical surfaces. And this spherical surface is what we call as spherical wavefronts. This spherical surface is what we call as spherical wavefronts. This spherical surface is what we call as spherical wavefronts. So I see the locus of point lying on this particular spherical surface, which oscillate with the same, with equal amplitudes with the same phase, all right, is what we call as spherical wavefront. So I have shown you 4 different spherical wavefronts, and this is the first. This produces this next spherical wavefronts. Second produce the next, that is third spherical wavefronts. Third produce a next, that is a fourth spherical. This is how light travels. And a wavefront is the locus of all adjacent points at which the phase of a wave is the same. A spherical, this is what we have done. The electromagnetic wave in the vacuum also spread out as shown here. This is what we have. This is how light travels like this. Alright. So this is what I have. First example. And this is this previous one is the 3-dimensional representations. This is the 2-dimensional representations. This is the source of light. And this is the first spherical surface. We call it as first spherical wavefronts. This is the second spherical surface. This is the second spherical wavefronts. This is how it goes. This is how it propagates. And we say that the speed of wave is equal to a speed of wavefronts. A speed of a wave is equal to speed of wavefronts. So speed of wave is equal to wavefronts, and the direction of a wave, right? So direction or the velocity of a wavefront is always perpendicular to the wavefront. This is what we have. All right, and this is what we call as a spherical wavefronts. Yes, this is the first wavefronts. I can have a sphere like this. This is a second spherical wavefront. This is a third spherical wavefront. I choose a small portion of a huge spherical surface. When you choose a small portion of a huge spherical surface, the surface looks plane. So let's say if I choose a small portion of a huge spherical surface, the surface appears plane. Again, I am repeating. If I choose a small surface from a huge spherical surface, then the surface appears plane, and this is what we call as plane wavefronts. So normally plane wavefront is again spherical. However, this is a small portion of spherical surface, spherical waveform. So this is what I have. This is how plane waveform. So this is how it travels. Alright, this will give you this will give you this. This is how it travels. So first wavefront produce, second wavefront, next wavefront, and then next wave. This is how it travels. So therefore wavefront is nothing but disturbance. And I told you before that when Huygens proposed these theories, he assumed that light is a mechanical wave, and this is how light travel in a space. All right, this is what I have. This is a plane waveforms. Now I would like to do Huygens constructions. Huygens constructions. Huygens constructions. Huygens waveform constructions. Huygens waveform constructions. So look at here. Whenever we use Huygens principles, all right, we always say that we should know initial waveforms. We should know initial waveform. Let's say that at a time at t is equal to 0, that is initially, if you know a waveform, right? Initial waveforms. If you know initial waveforms, if you know our initial waveforms, then you can construct a successive waveforms. Then you can construct a successive waveform using Huygens principles. How are you going to construct? So let's say I say that f at t is equal to 0, f1, f2 is a spherical waveforms. Is the initial spherical waveforms. I say initial spherical waveforms. Initial spherical waveforms. Oh, this is what we say a primary waveforms. Alright. Now, when we talk about Huygens, Huygens says that every point on a wavefront act as a source for a next wave, a spherical wavelet. So this is what we call as a spherical wavelet. This is what we call as a spherical wavelet. This is what we call as a spherical wavelet. And so I have so many spherical wavelets. Look at here. Each point, every point on a first wavefront act as a source for a secondary wavelet. This is what we call as a secondary wavelet. This is going to be a sphere. This is going to be a sphere. That is what we call as a spherical wavelet. Spherical wavelet. And again, one more important concept regarding Huygens principle is it is a geometrical constructions. You use a geometry and then construct waveform. Alright. So these all are these give rise wavelet, spherical wavelet, and corresponding wavelet. And I am going to draw common tangents. When you draw a common tangent, and now G1, G become G1, G2 become a secondary wave fronts. Secondary wave fronts. So this is how it. Now once you get this, alright, I say if a velocity is, if v is the velocities and if tau is the times, the distance traveled is going to be v into tau. This is the dead distance. Alright. And look at here. The velocity, this is the directions. This act like a ray, and the direction of propagation of a wave is perpendicular to wavefronts. Again, I am repeating. The direction of a propagation of a wavefront is perpendicular to the wavefront. So look at here. This is how it travels, and it is perpendicular to the wavefronts. So this is G1, G2 is a secondary wavefronts. Now, if you want next wavefronts, again G1, G2 act as a source for next secondary waveform. So I write here G1, G2 act as a source for next secondary fronts. So this is what? This is how wave travels. And this is what we call as a spherical wavefront. So this is the common tangent. This is the common tangent, right? This is the common tangent. Alright, so this is how you construct a wavefront. Again, so you go on, and this is a wavelet. Alright, you could produce, each point produce a spherical wavelet, and you get so many spherical wavelets, and you draw a common tangent, and that common tangent is none other than wavefronts. Alright, so therefore F1, F2 is a spherical wavefront at time t is equal to 0, and I'll explain you later, backward. Again, I have this. This is the wavefront again, right? This is the original wavefront. That is the first wavefront. Again, I am repeating, very important concept. This is the first wavefront, and then every point, this point acts as a source code. This is a wavelet. A spherical wavelet, and every point produce a corresponding spherical wavelet, and I draw a common tangent. This is a new wavefront. I call as a secondary wavefront. This is how light propagate in a space. This is how light propagate in a space. Now let's talk about a plane wavefront. Let's talk about plane construction for plane wavefronts. So this is plane wavefronts. I say this is a plane wavefront. This is a plane wavefront, and every point. So this produce a spherical wavelet. This produce a spherical wavelet. This produce a. You can have an infinite number of spherical wavelet, and I draw tangent, and this is going to be a second wavelet. If I say if a time interval is tau, after tau, this wave travels this distance. Distance is going to be, velocity is v, tau is distance, tau is time. So this is how wave travels. This is how wave travels. So, and again, I can have like this, again, alright, again I draw a tangent. This is going to be a next new wavefronts. Next new wavefront. This is how wave travels. This is how wave travels. This is all about. And now let me tell you one limitation of a Huygens principle. And I told you, since it is geometrical constructions, he says that the amplitude of a fourth secondary wavelet is a maximum, that is finite, and he says that the amplitude of a backward wavelet is 0. This is his assumptions. That means he says that his theory could not predict or talks about a backward wave. So the wave doesn't travel backward, wave always goes forward. This is his limitation, right? So limitation is that backward v1, v2 is not possible according to his theory. So this is the one limitation from his theory. So that means this is not possible for his theory, right? According to his theory, this is not possible, right? This is not possible. Actually, it is possible. Alright, so you can have, right? If I put a light, if I put a sound travels in this direction, also sound travels in that direction, right? So that he was not able to construct such a wavefront. So therefore, he says that it is not possible, and the amplitude of a backward secondary wave is going to be wavefront is going to be 0. So therefore, it is not possible, right? So this is all about Huygens principles, and this is all about how we construct Huygens principle, right? How we construct wavefront. And last what I'm going to tell you is, this is a plane waveforms. After some time, this travels like this. After some time, this is how it goes. This is how wave travels as far as a plane wave is concerned. As far as a spherical wave is concerned, this is the first, then it goes like this, and then it goes like this. This is how a wave travels. So this is how wave travels, right? So with this, I'm going to stop Huygens principle, and then in next class we will use the Huygens principle and study refractions and reflection. Thank you.